France, and 2014 Young Scholar Award, Foundation of Chemistry Taiwan, and so on. And professor is having for H index of 46 and citation more than 7,000. With a small introduction, now I request Professor Gerlio to take over the session. Please, sir.
Thanks. And first of all, let's welcome all the participants. And today we will have one theme talk and one invited talk, followed by 3 contributed talk. And let me introduce the first speaker. Professor Feng Yuanping has been working in the Department of Physics in National University of Singapore as far as I can remember. And he has been the chairperson and various administrative positions in the university. And for our community, he's also known as a very kind person and very productive scientist. I think the updated H index is 75. And yeah, I checked his publication list. It took me a while to go through the Google Science scholars. And I think today he's going to share with us some of the computational effort on the 2-dimensional material. And without further delay, let's welcome Professor Feng Yuanping.
Okay, let me try to share my. Okay, thanks, July, for a kind introduction. And thanks to Surya and the organizing committee for this kind invitation, for the opportunity for me to present some of our recent work. So I'm very pleased to see everybody here, even though we still have this COVID pandemic going on. I think it's nice to meet virtually in a space like this. I apologize for the change of the title. I just told Surya somehow I made a mistake in the communication. I sent the title to her first, and later on when I submit the abstract, this is the title I used. So I think I stick to this this version. That one was a talk I gave at another conference in November last year. I thought it's better to talk something new instead of talking about the same thing. Okay, so we have been working on a database for 2-dimensional materials. I guess these days no need to introduce 2D materials, and they are interesting, and due to this unique atomic thin layer structure, so they have very many different interesting properties. So a lot of applications have been proposed, and now the challenge is really make the materials and see whether they are really useful in many of the proposed application. Compared to 3-dimensional materials, I think the set of 2D material is still quite small, and particularly the experimentally synthesized 2D materials, is quite limited number. So it is important for us to continue to explore, design 2D materials and study them, see whether they are useful, they can be used for certain, future technologies. In this respect, I think data-driven approach may be useful, in helping speed up the discovery of two-dimensional materials. So with this background, a few years ago, we decided to work on a database for 2-dimensional materials. So the plan is to, collect structured properties of 2-dimensional materials, store them in a database, and then we can do, analysis of the properties, structures, okay, try to discover maybe some hidden physics correlations. Ultimately, of course, we want to explore application of this, 2-dimensional materials. So over the last few years, I think we have made very good progress. So first of all, we have been, designing two-dimensional materials using mainly two approaches. One is so-called top-down approach. That means we go, through the three-dimensional materials database, looking for layer structures. Then we isolate one layer, optimize the structure, and calculate the physical property. And then if the structure is stable, we store them in our database. The other approach, we refer to it as a bottom-up. Here, we basically start from known two-dimensional materials, then do elemental substitution. As an example, we can start from layered boron nitride. We can replace boron by aluminum, by gallium, by indium, and so on. And we can do the same for nitrogen, replace it by phosphorus, arsenic, and so on, so that we can get structures like boron phosphide, boron arsenide, aluminum nitride, gallium phosphide, and so on. So this is a way to generate enormous amount of 2D structures. Of course, some of them are stable, some of them are not. So for each structure, we do structure optimization and check their stability. If they are stable, we store them in our database. So the database currently contains more than 6,000 structures we got using the two approaches, and the structures and properties are freely available. So all of you are welcome to go to the website. The URL is given here, 2dmatpedia.org. So if you are interested, we can collaborate in this project. So all these are welcome. Today, I'm going to focus on 2D alloys, which is an extension of the database. We know that alloy is a very useful method. You can simply mix different materials, end up with properties, you beyond your expectation. A traditional example used in industry, people can combine different metals and then end up with a steel which has fantastic mechanical properties. And in the middle figure here, you see another example. So here, simply mixing cadmium telluride, cadmium selenide, you can have a ternary compound, and the band gap variation actually goes beyond the band gap of cadmium telluride and cadmium selenide. Okay. Of course, this has also been explored for 2D materials. So as shown in this figure taken from this publication. So mixing, I can see this, cannot see this. Okay, mixing moly disulfide and moly diselenide by varying sulfur and selenium composition, you can achieve a variation of photoluminescence over a very wide range. So this is why alloy is something very useful. Okay, when we started working on this, we have a kind of a naive thinking. We all know that carbon phosphorus among the two very well studied 2D materials. And they are both single layer elemental 2D materials. But graphene carbon is a flat structure. Phosphorus, the most stable structure, is in this puckered form. Then the question is, can we mix them? And if we can mix them, what will be the structure and what are the physical properties and how the structure and property evolve with composition? Actually, another 2D material is arsenine, okay? And here, the structure is in the buckled form. So we can ask the same question, can we mix arsenic with carbon, arsenic with phosphorus? Similar questions. And furthermore, can we mix 3 elements to form a ternary alloy? So this was our motivation. Actually, in recent years, people have looked into, possibility of forming monolayer phosphorus carbide. Most of the study I think, focus mainly on the phosphorus carbide with the 1-to-1 phosphorus to carbon ratio. Now, in this kind of a structure, we all know carbon somehow prefer sp2 bonding. Phosphorus prefer sp3. So when you mix them, there's this competition between sp2 and sp3 bonding. And because of this, the structure could be very complicated. So in various studies, they propose many different structures. These are just a few taken from the literature, okay? It is interesting that this is a work actually from my colleague in engineering faculty in US. They managed to grow a few layer phosphorus carbide using this method. Okay, I will not go into the detail of the method. So the characterization shows that indeed there's a layer of a phosphorus carbide grown between, on top of the black phosphorus. And furthermore, they proceed using this material made a FET, okay? And it turned out that this device, based on few layer phosphorus carbide, they have a very high responsivity and short response time. So this means the device can be very useful for high speed, for weak signal sensing, okay? Quite recently, there seems a lot of interest in this type of materials. Quite a number of papers published last year, as you can see from here, and they look at the formation. They also propose many applications, and there's even one paper already this year, okay, in Journal of Energy Chemistry, and so on and so forth. And quite recently, there's another paper in Science. Basically, they use this black phosphorus graphite composite. They found that this is something very useful for high rate, high capacity lithium storage. I'll come back to this one later on. Anyway, I can see that all this motivated us to look into this, but actually we started our work before that. Anyway, I think all those recent activity interest confirm that this is something worth to be explored. So from the literature, people predict that this kind of a 2D alloy, phosphorus carbide, they have a superconductivity. They show quantum Hall effect, high carrier mobility, and as I mentioned, a lot of application already predicted based on this 2D phosphorus carbide. But on the other hand, most of the theoretical studies, actually most of the studies are theoretical except a couple of work I mentioned, which are experimental. Many of the studies basically done using DFT, typically with a very small supercell. That, of course, they claim is stable, but who knows what will happen when people try to grow this, okay? So the question is, can this material really be produced, okay? Another thing is the previous study I mentioned is mainly focused on 1-to-1 phosphorus to carbon ratio. And the question is it possible to grow this kind of material at any arbitrary composition, and how the physical property vary with the composition? So these are the questions we try to answer. So what I'm going to present in the following is part of a PhD thesis work of my PhD student Xiaoyang Ma, who just completed her PhD study, now back to China. So we are trying to, still in process to get this result published, okay? The method used to study alloy in 2D, 3D, they have been around for quite some time. So this is very standard. So we use DFT to, calculate the energy of some structure generated using certain method, okay? Then we, use this cluster expansion method So use the DFT data as training data to train this model, basically to determine the coefficient in the expansion. And then the thermodynamic property can be calculated using this Monte Carlo simulation. So it's a very mature method. I will not go into details. If you are interested, you can look at the reference given there. Okay, this is how we go. For 2D carbon, there's only one stable structure, which is graphene. But for phosphorus, there are 3 or even more structures. Their stabilities are quite close. The most stable one is black phosphorus, but the energy of a blue phosphorus, gamma phosphorus look like that. Their energies are not very high, compared to black phosphorus. So we are thinking about designing 2D alloys. That means we should also consider these relatively slightly less stable structures. They may be stable when we mix phosphorus with carbon, okay? So using the method I just described, we start from each of this structure given here, then basically try to build an alloy, using the method we just described. So this is some results from the calculation. What you see here is basically the formation energy of the mixture, relative to the energy of a separate phosphorus and carbon. So the first figure is for using graphene as the parent lattice. This is using black phosphorus. This is for blue phosphorus and gamma phosphorus, respectively. So some numbers here. The number here, basically the structures we started using DFT. And these are the number of structures predicted using the cluster expansion method. So to see whether there's how reliable, we use this cross-validation score. These are the relevant numbers. So anyway, I think you have to trust me that the results are reliable, okay? Now, a couple of things we can see from this figure. The formation energies, they are all positive. That means we need to provide energy in order to mix the two materials, okay? Secondly, the smallest formation energy, as you can see from the figure, is above 0.1 eV. And that, from a thermodynamic point of view, is quite high, okay? So the first conclusion we draw from this result is that probably it's going to be difficult to form alloy or mix carbon with phosphorus. So we further proceed to calculate the temperature composition phase diagram, which can be done using this Monte Carlo simulation. Well, the phase diagram looks pretty boring. And across the whole composition range, up to very high temperature, you only see a phase separation region, okay? So that tells us it is probably very difficult, if it's possible, to grow two-dimensional phosphorus carbon alloy. You see, some bending of the phase boundary at very high temperature, but that only occurs at very small x or very large x. So this is basically you dope phosphorus into carbon, carbon into phosphorus. It's not really an alloy. Actually, people studied, diamond-like film, tried to dope phosphorus into that. It was not easy. So I think, this is the reason. So this sounds discouraging. We want to form alloy, and the conclusion is this is impossible. Then what about the ordered structure? Those structures studied in previous theoretical works. Okay, can they form? With this question, we gone through a systematic study we refer as a bottom-up design of ordered phosphorus carbon structure. I don't use the term alloys anymore because it's not really a random alloy. Okay, So in this case, we use supercell up to 16 atoms. And then we basically consider all the possible configurations. And then for the distinct structures, we calculate their energy, try to find out what is the minimum energy structure. So just example, using graphene as the basis structure. Suppose I want to generate structures for 25% phosphorus, 75% carbon. So within this 2x2 supercell, 8 atom, I have to produce this composition, I need to substitute 2 carbon by phosphorus. I can put 1 phosphorus here, then the other one can go here, 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 or there. So there are 8 configurations. Of course, some of them are equivalent. For example, the last one is equivalent to this one. So in this case, we just keep 1. So we went through this process. It's quite tedious. So my students spent a lot of time. We considered supercell up to 16 atoms. We end up with 2,000, more than 2,000 distinct structures. Then we perform DFT calculations for all of them. And this is the result. This is the formation energy represented as a function of a composition. So basically, you see a similar picture as you saw in the earlier Monte Carlo, the cluster expansion result. So all the formation energy for all the structures are positive, and the values, it's 0.2 and above. So this conclusion again is difficult to form this kind of a even the ordered alloy. Okay. Then we look at the structure correspond to the minimum energy, which is indicated by the red square here. So for each composition, we pick the lowest energy structure, which is supposed to be most stable structure. And this is how they look like. This is for 12.5% phosphorus, 25%, 35%, 35.7, 37.5%, and so on, okay? Now, you see 2 distinctive features. One, you see clear phase separation. You see the carbon atoms are clustered together, and so are the phosphorus carbon. So this agreed with earlier, conclusion. They don't like to be mixed. They prefer to phase separate. But within a supercell of a 16 atom, this is indicated by the rectangle, and this is all they can do. Okay. Secondly, you find that the carbon and phosphorus, they form vertical strips. You have to think about there's a periodic boundary condition here. So then it's easy to imagine that the carbon will form a vertical strip in this figure, and so is the phosphorus region. And this is actually, if you look at the detail, they are armchair graphene nanoribbon, and these are armchair phosphorus nanoribbon. If you look at the structure of the phosphorus, this is actually black phosphorine. Okay, so these are the most stable structure at each composition. In our calculation, we also considered blue and gamma phosphorus, but you don't see them here. That's because their energies are higher compared to black phosphorus. So this means that if we find a way of growing these things, and probably you end up with this kind of a structure rather than the structure built using super small supercell. Okay, so the conclusion we can draw from here is it will be extremely difficult to synthesize the ordered structure like this started in earlier theoretical work. Okay, so this again is discouraging. But anyway, okay, within the supercell of a 16 atom, and we got this kind of a structure. Basically, they are superlative structures, consist of a alternating graphene and black phosphorus nanoribbon because they are periodic boundary conditions. So these are periodic superlattice structures. So from now I refer them as superlattice structures. Then we further looked into the stability and physical properties. So we did phonon calculation, and even sometimes we see a small, imaginary frequency near the gamma point. We assume that this is, something due to the finite supercell. Hopefully, can be, eliminated using a larger supercell. Of course, we have not done that. We run molecular dynamics simulation, ab initio molecular dynamics simulation. Basically, they are stable. The calculated electronic structure shows that the band H typically, consists of a contribution coming from both carbon and phosphorus, and typically these are from the atom at the H between the carbon and phosphorus nanoribbon. I can show you my time. Let me just quickly show you some of the molecular dynamics simulation result. This is at room temperature, and you see the atoms, fluctuate, but the structure basically remain intact. And this is 300 Kelvin. We even did simulation at a higher temperature, and the fluctuation is larger, but the structure essentially remain unchanged. So we conclude that I don't know how to grow this, but we conclude that once this kind of structure is grown, they can be stable. So they can be used for device application. So this is our conclusion. It is interesting in the recent science paper using black phosphorus graphite composite for high rate, high capacity lithium storage. As you can see from the figure at the bottom left, they do observe the detail of the structure consists of a interface between black phosphorus and graphene. So this is the model they proposed, and actually it is the interface that actually promote this kind of a functionality. So this, I think, first suggests that this kind of a structure probably can be grown. Secondly, and this kind of a structure probably is useful. For example, for lithium storage, they can use this, composite. Probably they can use our proposed superstructure. We also looked at, how the physical property vary with compositions. For example, we look at the change of the band gap with composition, and we also try to compare with the data we collected from the literature. This is GGA PBE band gap. You can see that they fluctuate in a wide range, and our data basically, within this range of fluctuation. And furthermore, you see this kind of a oscillation of the band gap. And this can be actually explained using the band gap variation with our width of armchair nanoribbon, and as well as armchair graphene black phosphorus nanoribbon. So this is understandable because the superlattice consists of a nanoribbon of graphene and black phosphorus. We also see, some band gaps are direct, some are indirect. This again can be explained based on, finding from previous studies. For example, if you see the band gap, evolution of armchair graphene nanoribbon, this is for 13 atomic chain wide. When you increase the tensile strain, you can convert a direct gap into indirect gap. I have not found any data for phosphorus nanoribbon. This is from 2D black phosphorus. So this shows that a strain along the armchair direction can also induce direct to indirect gap direct to indirect gap transition. So this probably provide explanation here. I think I should leave some time for discussion, so I will not go into details for this is mechanical property. So again, this can be explained why it's isotropic in carbon-rich structure, but it's anisotropic in phosphorus-rich structure. We also calculate the mobility and optical property. That's it for phosphorus carbon. And we also studied, other structures. This is actually done by a visitor in my group. And the silicon germanium was also done by my PhD student. Silicon germaniums are relatively similar. Their structures are similar, so we expect they should be easier to be mixed. And the calculation indeed conclude that at low temperature, they still phase separate, but at higher temperature, they can be mixed. And furthermore, in this kind of alloy, somehow the Dirac cone is still there. This can be, explained, but based on the model from previous studies. So I'll stop here. I will not read the conclusion, but I need to thank the people who have done the work and the agencies provided the funding for our study. Thank my collaborators also, and thank you for your attention.
Yeah, thank you. I think we got the question from Professor Kwangyo Lee. For his question is, can the user upload their own calculations to this 2D database that you mentioned, so that we can make a bigger database?
Can you
can the users upload the right? You mentioned the 2D database you generate, and Professor Lee's question is, can the user how would the users interact with this database? Can they upload their own calculations?
Yes, we'll upload all the structures to the 2D material database. This is in process.
Okay. Now, any questions from the audience?
Yeah, Jedlai, this is GP here. Can I ask a question?
Yeah. Please.
Yeah.
GP, please.
Okay, Yuan Ping. So nice talk as
Thank
usual.
Thank you.
Yeah. I would like to ask, about I have some query about this phosphorus carbon. Interesting, albeit a little bit controversial, but still, I mean, purely from the point of view of the electronegativity, I mean, what is the kind of a charge transfer that have you noticed between phosphorus and carbon? The charge transfer.
If you look at the structure in the graphene region, it's basically similar to graphene. So you still have this pi bonding, and in the phosphor region, you have this lone pair. So the charge transfer is not significant.
Well, that is expected because the electronegativity difference also, I mean, is not much between the two. I mean, yeah, so that is expected.
Yeah, that's why the property is mainly, dictated by the graphene nanoribbon, phosphorus nanoribbon, particularly in carbon-rich, phosphor-rich region.
Yeah, yeah, okay.
Yeah,
the other question which I have is, you mentioned about the cluster expansion method. Now, in order to do the cluster expansion, you need to have the input with some of the ordered structures, But
yes.
Yeah, so in order to carry through the cluster expansion, you need the ordered structures. Now, what are the ordered structures that you have that you can give as an input? Because the phase diagram shows a very peculiar, phase diagram.
There's a systematic way of generating representative structures. So we use this algorithm.
I see.
So they have studied, how to, sample the structure so that you get a collection of structure that is representative of the
No, this is for silicon germanium. I mean, you in the same thing you have used for phosphorus carbon. This is
For
particular.
the cluster expansion, yes. For the super structure, we basically consider all the possible structures.
Yeah, but
Okay.
but the lowest structure that you have shown in one of the phosphorus carbon, these lowest structures are the theoretically achieved lowest structures. But somewhere you have shown in one of your slides, the blue dots. You have shown the lowest structure for each. Yes, here. Yeah, the red ones. Yeah. So the red ones are the lowest structure corresponding to different compositions.
Yes.
So are these sort of structures your inputs for finding out the cluster expansion?
Yeah, I understand your question. This is not, we're not using cluster expansion here. This is basically, we exhaustively consider all the possible structures. So for example, at x equal to 0.25, all the possible structures within the limit of a 16 atom supercell are considered. So there's no more. This is quite conclusive.
Yeah, I hate to cut short because there are a couple of questions from.
Okay, thank you.
Professor
May I ask one question here?
And Professor Kumar,
Are you asking? Hello.
Yeah.
So I have two questions. One is that when you have PC alloy or ordered structure, so will it be a better absorber of lithium compared to, let's say, graphite or some other structure? Why one should go to such a complicated system?
At the moment, we are just interested in whether we can mix phosphorus and carbon. As you see from our plan, we want to look into application, but that will be the next thing. At the moment, we have not considered lithium or not considered anything else. So if you're interested, we can work together.
Okay. One more question is that you said band gap opening. So in graphite, so we showed several years ago, 9-10 years ago, that when we doped boron nitride in graphene, there was also band gap opening because of the confinement. So I was just wondering that we said that it's a general phenomenon that if you will dope and then this nice periodicity of the graphene is broken, and that would lead to the band gap opening. So I just wanted to make a comment on that.
Yes, I would think so, because I think this is a combine of a quantum confinement, the carbon phosphorus age. There's also a little bit strain in the system. Yes, it's kind of a combined effect.
We also did something like similar strips. I will send you the paper.
Yeah,
that will be interesting actually. So thank you.
So I didn't have time to go into detail. For example, when we replace actually 2 carbon by phosphorus in this 60 atom supercell, the band gap jumped to close to 1 eV.
Yeah. We also found that maybe more than 1 electron volt band gap.
Yeah, I think it's consistent.
We will let Professor Kawazoe ask the last question, hopefully short.
Very short. Yuan Pin, you belong to a 2D laboratory and you should have experimentalists nearby, and you propose many things, good properties, but some of them are difficult. For example, we propose pentagraphene, 5 years, no sense. So you should discuss with experiment, or already have you negotiated with them? They know which is easily synthesized, and some of them are difficult, something like that. Please explain your situation.
Excellent suggestion. Yeah, we'll definitely do that. Thank you.
Thank you. So with that, I think I'll conclude Professor Feng's talk. And I think it's nice talk have attract more than 55 participants now.
Thank you.
Okay, so with that, I will have the pleasure to introduce our next speaker, Professor Huang-Yo Li from KISS. Professor Li is a well-known figure in this community, and he's currently the head and the principal research scientist in the Computational Science Center of KISS, which is a premium research institute in Korea and in the region and probably globally too. And Professor Lee has a long CV, which I would mention one thing that in his research interests, for a few years, as far as I remember, he and his group has been developing web-based platforms, right, for not only the professional computational material scientists, but for other users to enter this field. And his research group cover a wide range of topics, ranging from the growth and to the design of the materials. And I think in this community, he's very well known and always energetic. And I remember if he get a chance to go to bring his bike, he will probably cycling around the city whenever he has a chance. And today, he's going to tell us some of the new results on the theoretical analysis of oxygen transport in the dope cereal. Let's welcome the speaker.
Thank you, Jorai. Thank you very much for kindly inviting me to this excellent conference. And it's very nice to meet an old friend on virtual, even if it's online, but it's very, very good to see you here. It's already for last 1 year, we have never met again. So I think this is a very good chance for meeting here. Okay, let me share my presentation. Today I talk about the, okay, so now can you see this?
Yes.
Right. Okay.
Yes, we can.
Where is the, all right.
Pointer.
This one. Okay, I'm not familiar with this system. So anyway, where is my can you see my pointer?
Yes, we can see
right.
your cursor pointer. Yeah.
Okay. So today I talk about our for last couple of years I've been talking about the platforms that can provide a very easy to use working environment for not only computation people, but like some experimental people. I want to invite many experimental people can do their own computation on our platform. And that platform is on your this stamp. This is a vfab.org. That is our portal site for the platforms. So if you visit there, you can find many interesting platforms that you can utilize for your own research. And but today I talk about I'd rather focus on some computational work about oxygen ion transport in doped celia. Doped cilia is widely used for solid oxide fuel cells, and our calculation shows the significant effect of Bacon's trapping on the ion. So this work was done by my postdoc, Emin Kirik from Turkey. And also we are collaborating with experimental people, Dr. Chong-Hori and myself. So if you have a question about this work, please send me an email. All right. So you may know that solid oxide fuel cell is very interesting devices to generate the electricity from the very clean fuels. And this is I think this is a very important device for our futures. This is very eco-friendly. And as you can see on the right side, comparing to other electric generating devices, SOFC is the highest efficiency, has a highest efficiency material, highest efficiency devices, and it doesn't need the precious metal catalyst as in the PEM fuel cell. And also it has a highly flexible the fuels, but the only problem is it should operate at high temperature. For these solid oxide fuel cells, the materials, the most popular materials are for the anode side where the reduction occurs. I'm sorry, oxidation occurs. The nickel doped yttria stabilized zirconia is widely used. And then the cathode side, the strontium doped lanthanum manganate was widely used. And the electrolyte is very, very important to determine the transport of oxygen ions from cathode to anode. That is the yttria stabilized zirconia is widely used. But the system is usually operated at very high temperature. It causes many problems. So this is the schematics of the fuel cell stack. It has many electrodes, and also it has a sealant. And there are 3 ceramic plates, anode, electrolyte, and cathode is combined here. And also another gas, the so-called gas flow unit and the sealant. And it's composed of these complicated structures. Because of high temperatures, the anode, electrolyte, and cathode materials suffered from the microstructure change and even breaking, as you can see here. And on the metal interconnectors usually have under the severe corrosion environment, and the sealant is easy to degradation by this at these high temperatures. So engineers of SOFC want to operate this device at much lower temperatures. But all the reactions occurs in this device is of course the chemical reaction, which is very sensitive to temperature. The device performance degrades very rapidly if we decrease the temperature. This is the case of voltage. Of course, this is schematic, but all the current range, the voltage drops and also power drops very rapidly as we decrease the temperature. So in order to achieve the low temperature operation at stable and very high efficiency, we need to very, very thin electrolyte. This is so that we need to have a high ion flux of oxygen even at low temperature. And also, eventually, we want to make new materials with a higher conductivity for electrolyte and also cathode and anode materials. But as I said before, electrolyte is the most crucial to determine the performance of the fuel cell. So this is some schema, some graphs that shows the general operating temperatures and total conductance of these materials. In the case of ceramic membranes usually operate at high temperatures, but gadolinium doped ceria, if we use the gadolinium doped ceria as electrolyte, the conductivity increases very high even at low temperatures. So if we draw the same conductance, the cells can be obtained at very much lower temperatures than yttria stabilized zirconia. So gadolinium doped cerium oxide is a very promising materials for the electrolyte materials. So our work is focused on this gadolinium doped cerium materials. So this is some simple chemistry about the doped cerium materials. In these systems, we usually doped trivalent dopants and replace the ceria for quadvalent ceria. And by these dopants, the oxygen beacons generated for to make a charge balance. So in generally 2 trivalent dopants and 1 oxygen vacancy was generated. And this oxygen vacancy is very essential for the oxygen diffusion in this system. So the kinetic behavior of the oxygen vacancy is crucial to the oxygen ion conductivity. But it is in this community, it is widely known that this dopant, generally dopant and the vacancy interaction is very strong. So that the cation, the doped cation has a generally 2 effects. One is because of the size of dopant is different from Syria as cesium. No, not cesium. It's a cerium. So it will distort the lattice. So it affects the vacancy migration by increasing the energy barrier of the oxygen vacancy migration. So this is called by blocking effect of the dopant. And also there is a strong association between the oxygen vacancy and the dopant. So this tend to attract the vacancy to the dopant. So it will hinder the oxygen vacancy movement. So this is called the trapping behavior. But in many previous work is focused on to understand these 2 phenomena in these systems. But it's very, very difficult to isolate each effect. It's very difficult to understand independently each effect of this phenomena, because this is closely linked by the physical property of dopant and vacancy. So in the present work, we want to study the blocking and trapping independently. So we studied the co-doping effect on the vacancy diffusions. And using this method, we think we can study independently of the blocking and the trapping behavior. So this is in the present work, we first characterize the 10 more % gadolinium doped Syria. In the short term, it's a 10 GDC. We express this. We use this method, and we focus on the co-doping effect of vacancy diffusion. So we co-doped yttria, 3% of yttrium and lanthanum, and 7% of gadolinium doped in Syria. So total doping amount is 10 more %, but 3% was replaced by this. So we want to compare all these things and try to understand the vacancy diffusion behavior. And eventually we want to understand how much the trapping is important and how much the blocking is important to understand the oxygen vacancy diffusion. So we applied both statistical molecular dynamics simulation in large scale, and also we applied the first principle calculations. For the first principle calculations, we used a 2x2x2 supercell of gadolinium doped Syria, and this case is about 12.5 more % of gadolinium doping case. It's similar, but you cannot exactly make a 10 more % gadolinium doped Syria in first principle calculations. But in molecular dynamics simulations, we handled 12,000 atom systems, so 4,000 cerium and 8,000 oxygen ion systems. And among them, 400 gadolinium was substituted to cerium. And the 200 vacancy was introduced into this system for charge balance. And for the co-doping systems, we replaced 120. We introduced 120 yttrium and 120 lanthanum to these systems with 280 gadolinium in this system. So this is exactly 3Y7GDC and 3 lanthanum 7GDC case. Okay. So gadolinium is among these dopant is so widely used in the cerium the ion transport study, And the gadolinium is known to have a highest electron conductivity than others systems. And some people said this is the gadolinium. This is because gadolinium is the size of gadolinium is very similar to cerium, so that the gadolinium introducing the gadolinium doesn't change a lot about the blocking behaviors. But yttria and the lanthanum has a different. The size of yttrium and the lanthanum is different from the cerium, so that it will cause many large distortion in the lattice, so that it can actually block the oxygen ion diffusion. So in our systems, okay. So for in this work we DFT calculation using the BASF, and this is a typical calculation conditions, and also we use the NEV calculation for energy values of oxygen diffusions. We also use the NEV calculation method. And for the molecular dynamic simulation, we use both SCULP and the LAMS code for the lattice dynamics and molecular dynamics respectively. In both cases, we use the Buckingham potential with long-range Coulombic terms. And this is generally accepted to describe where the cilia and many oxide material systems. And in this work, we apply the coordination number analysis to characterize the trapping behavior of the bacons to the dopant. And for the better statistics, we use the 5 different configurations of the same concentration. And also we use the diffusion analysis by mean square displacement and the Einstein relationship method, so that we can using this data at at wide range of temperature, we can calculate the energy barrier for the diffusion directly. Okay. This is the interact potential parameter that we use. The Buckingham potential is composed of these two terms, including the band bars, and but in this, for the ionic system, we also include the Coulombic interaction. So the parameters is composed of 3 parameters: A, rho, C in this equation, and these values is widely used for the molecular dynamic simulation of this ionic system. So first of all, we did the equivalent configuration of GDC, and for the GDC calculation, equivalent configurations, we used the 2 by 2 gadolinium doped cilia, and we introduced 12.5 mole percent gadolinium, as I said before. And all the possible configuration is 43 millions, but using the side occupation disorder algorithm, we can reduce the number to 145,000, and 145,000 system was calculated using the lattice dynamics. So each gadolinium configuration has 2016 oxygen vacancy configuration. So we calculated all these systems. So we found the lowest energy configurations, as you are expressed, as I represent here as a blue dot. And then using these blue dots, we apply the density functional theories to calculate the lowest energy configurations. And we found this is the lowest energy configurations. And the lowest configurations definitely shows that oxygen vacancy is closely associated to the dopant. This black atom is gadolinium dopant, and green is the vacancy. So we confirm that there is a strong interaction between oxygen vacancy and the doped cation here. So this oxygen vacancy interaction has a deleterious effect on the oxygen diffusion, because this vacancy is hard to move once it is associated to the doped ions or other vacancies. So anion diffusion need to overcome the trapping of the oxygen vacancy to the doped ions. The reduced preference of oxygen vacancy would increase the mobility of oxygen vacancy. So the understanding the association behavior is very important to predict to find the better dopant for this system in terms of the oxygen ion diffusion. So this is the result with the 10 gadolinium doped system and the 2 co-doped systems, and we found a very interesting result here. The equilibrium co-doping equilibrium coordination number would be the 8, and if this is a perfect crystal, but because of dopant, there is many vacancies. So the coordination number of cerium is down to 7.8, but gadolinium has much lower values than this one. It means that the vacancy is preferentially associated to gadolinium. So gadolinium, even if gadolinium can generate the vacancies to increase the oxygen diffusion, but gadolinium has also have a deleterious effect of the diffusions by strong association. And this, but if we add the yttrium has a lower than the gadolinium. So this means that yttrium has a more stronger. There is a stronger association to the yttrium than gadolinium. So yttrium is a stronger effect of trapping the vacancies here. But in the case of lanthanum, it's the opposite. Lanthanum is lower trapping behavior tendency, and so that this means that the vacancy can be more mobile in lanthanum than yttrium and gadolinium. So that so we think I not have enough time. So let me show the diffusion simulation result. This is a 10 GDC case. In the 10 GDC case, we found that the activation energy is 0.72 electron volt in this system. So of course, this is some movies that I can show you, but I think I'd better skip this part. So for the if we co-dope the yttria and lanthanum, if we add the yttrium, the energy the activation energy is larger than the gadolinium, and in the case of lanthanum is smaller than gadolinium. So this has a consistent with the coordination number of these systems. In the case of yttrium, vacancies is more strongly associated to the yttrium atom, so that there is a smaller number of mobile vacancies in this system. But in contrast, in lanthanum cases, the lanthanum has a higher coordination number, and means the less association of the vacancies, so that the energy barrier for diffusion is smaller than. So this result shows that there is a strong relationship between the energy barrier for diffusion and the trapping behavior of the vacancy to the dopant material. But in contrast, if we calculate the blocking of the dopant in all cases, it's a gadolinium doping or yttrium doping, or gadolinium yttrium doping and gadolinium lanthanum doping, and in all cases the blocking energy increases, because these all cases distort the lattice, and it's very natural to increase the energy barrier for vacancy jump from this side to the next side, so that our diffusion observation is not consistent with this blocking behavior. So our result shows that the trapping of the vacancy is more important to understand the oxygen diffusion in ion conductor material.
Kwangyo, two more minutes.
Okay, so I'm sorry, I didn't think this time was very long. Okay, characterizing the coordination number of the most important result of this work is that the characterizing the coordination number of cation and diffusion simulation in large scale disclosed the major factor to control the oxygen diffusion in Syria electrolyte. And we found that this diffusion is strongly dependent on the vacancy trapping behavior rather than the vacancy blocking behavior. Okay, that's all. Thank you very much for your attention. And I'm sorry I spent too much time.
No, perfect. Now the floor is open for questions.
Can I ask a short question?
Yep.
Sure.
During the molecular dynamics simulation, do you see the ions or the dopant clustered together, or they prefer to be dispersed?
So for the molecular dynamics simulations, so we actually, this is some example of the molecular dynamics simulations, and so we do not consider any clusters in this system. So we consider only in atomic scale.
Okay, what was the temperature of this simulation?
This is 1072. This is a typical operating temperature of the Syria system.
Okay, thank you.
1000 K, or it's around 1000 K. So the lead atom is, the lead ball is the oxygen, and the only oxygen move around, while the other cations are steady. So this is this means that the vacancy should detach from the doped cations for this kind of diffusion. So trapping of the vacancy is very important to optimize this system.
Can I ask one question, Kwangryul?
Oh,
okay.
Hi, GP.
Hi. Yeah. So yeah, I mean, nice presentation. I just thought of asking you that in your molecular dynamic simulation, something in a similar line as what Yuan Ping just now asked. Now, how important do you think is the fact that you are still doing the simulation within the harmonic approximation? I mean, because these are all at, the temperature plays a very crucial role. So I was just wondering whether, deviating from the harmonic deviation from the harmonic approximation is something which is important to be included in your calculation, or how much is the improvement one can expect if you go away from the harmonic approximation. Inclusion of the anharmonic term in the potential. See, you mentioned about this.
I see.
See, you mentioned about the Buckingham potential. Of course, that is
right.
which is a semi-empirical. Exactly. So
I think it should improve the result a little. It may affect the result, but I don't think it's very significant, because so using the validity of these potentials for simulating this system is confirmed in many previous papers. Also, it's an experimental result is quite consistent with this stimulation, with this potential. I think even if we include some additional terms, may improve something, but I think this potential is enough to understand this phenomenon.
Why I mentioned is that in magnesium oxide, for example, it has been seen that it is important to include the effect of the anharmonic term. So in the Syria, the cerium oxide also, there may be some angle dependent terms which are neglected in this. So I mean, it is just suggestion that in your simulation, if you can include, for example, I mean, the Stillinger-Weber kind of potential, okay, or Tersov kind of potential, which are used for semiconductors, where there is an angle dependent terms which are coming. So how important or unimportant is the fact that you are not including those in this?
So I think of course there is no 100% ionic materials, but of course this system also have some kind of a covalent bond characteristics,
yes, exactly,
which is important for the bond angles. But in these systems, the ionic characteristic is very, very strong. So in that case, the bond angle dependence may be limited.
Yes. Okay.
Kwagyo, there's a question from the audience. The question is, how do you experimentally identify oxygen vacancy? Experimentally. How would the experimentalists identify the oxygen vacancies that you have simulated? Is there any direct or indirect way? Or?
Experimentally, there is no way to distinguish the oxygen vacancies. So experimentalist, this is the only measurable quantity for experimentalist is the diffusion coefficient for diffusion activity. So for the, of course, for the computation people, so computation people can identify each vacancies for in our simulation condition. But in order to compare with the experimental result, we should provide some statistical properties that experimentalists can compare directly with their measurement. So in that aspect, I think the diffusion coefficient measurement is very important.
Right. Okay. Yeah, I also have some questions, but I guess in the interest of time, I would.
Thank you very much.
Yeah, thank you.
Thank you, Jorai. Thank you very much.
Thank you. If you have questions, you can write to Professor Lee. Then with that, let's move to the second part of this section. And we will have 3 contributed talks. And all the speakers here? Okay.
Contributing lectures speakers are available. Naveen Kumar?
Yes,
Naveen Kumar, yes, okay. Okay, can you please share your screen?
Yes, ma'am. Yes.
And give your presentation for 10 minutes. 8 minutes will be the presentation and 2 minutes for interaction.
Okay, ma'am. Okay. Ma'am, am I audible?
Yes, go on.
Thank you. A very good afternoon to all the delegates and participants present here. Myself, Naveen Kumar, I'm doing PhD under the guidance of Dr. D. Prabhakaran sir, Department of Chemistry, Vellore Institute of Technology, Vellore. Today I'm going to present one of my photocatalysis work entitled A New Age Photocatalyst based on zirconium oxide, silver oxide nanocomposite, which was uniformly dispersed into a polymer monolithic template. Coming to the introduction, due to the increase in the industrialization and the release of waste from the household has been increasing day by day, and which induces the water contaminations and which is one of the main problem we're facing here. So there are several techniques available in order to treat this wastewater, but there are some limitations considering the cost factor and the secondary pollutant that are released from these traditional techniques. Nanotechnology has been gained more attention. In particularly, heterogeneous photocatalysis has become one of the promising technique for the treatment of wastewater. However, one of the key point we observed here is the recovery of nanoparticles from the system, from the photocatalytic system is one of the challenging issue faced by this is due to because of low particle size and surface area that is attained for nanoparticles. So the current aim is to overcome the issues that are associated with the nanoparticles based photocatalyst, that is nanotoxicology and recovery issues. So to overcome all these, we made an attempt by synthesizing a new class of zirconium oxide silver oxide photocatalyst, and this photocatalyst was embedded into a macromesoporous translucent polymer monolithic as a adsorbent support, and this will tackle the issues that is created from the nanoparticle issue, that is recovery, and all the issues can be eliminated by embedding these nanoparticles into the solid sorbent. Coming to the objectives, initially we have to prepare the zirconium oxide silver oxide nanocomposite, and the fabrication of this nanocomposite into the polymer template was done by a simple free radical polymerization pathway. And in order to increase the photocatalytic efficiency, we have to do optimize the several physico-chemical parameters. Initially, coming to the synthesis part, the zirconium oxide nanoparticles was prepared using a sol gel method by taking zirconium butaxide as a precursor in the presence of hydrogen peroxide as a mild acid, and under controlled aging and calcination and under controlled hydrothermal temperature, we obtained zirconium oxide nanoparticles. And for the composite with silver oxide, we followed a simple precipitation method, and after synthesizing the zirconium oxide silver oxide composite at various compositions, the optimized stoichiometric nanocomposite was embedded into the polymer monolithic support by taking edema as a polymer precursor and AIN as a radical initiator in the presence of DMSO as a porogenic solvent. This combination of edema and DMSO porogen will create a translucent macro-meso combined polymer monolithic network, which will useful for the diffusion of light penetration into the active photocatalytic sites. After synthesizing the polymer monolith embedded nanoparticle photocatalyst, the characterization studies reveals that initially zirconium oxide at various temperature shows the amorphous nature at without calcination, and 250 degrees centigrade of thermal treatment, it was showing a monoclinic phase. After that, tetragonal phase was obtained. Considering the importance of monoclinic phase in the photocatalysis system, we taken the monoclinic phase zirconium oxide nanocomposite, and which was embedded with the phase-centered cubic silver oxide material, and the corresponding peaks was obtained in the range of 35 degrees and 40 degrees of, which confirms the presence of phase-centered cubic phase of silver oxide. And with the increase in the silver oxide content into zirconium oxide, redshift was noticed. This confirms the increase in the visible activity of the zirconium oxide photocatalyst, because the zirconium oxide has a large band gap which potentially works in the UV region, and the corresponding band gap was calculated from the tau plot derived from Kubelka monkey equation. Here the bare zirconium oxide was showing a 4 band gap energy, and with the dopant of 40% silver oxide, the band gap was reduced to 2.2, so which confirms that the photocatalyst will effectively work in the visible light. And coming to the PL analysis, the optimized 40% silver oxide zirconium oxide composite shows least PL intensity. This is due to the decrease in the electron hole recombination rate. And coming to BET analysis, the surface area of bare silver oxide zirconium oxide shows 64.54 surface area. However, with the embedding the composite into the polymer template, the drastic increase in the surface area was noticed, which is 254.85, and the pore diameter was maintained in the range of 3.46 with this mesoporous range, which confirms the mesoporosity channels present in the macroporous network. And the isotherm pattern was H1 starch loop with the di4 isotherm. The structural properties of the prepared nanocomposite and its embedded polymer monolithic composite was analyzed using SEM and TEM analysis. Here the figure AB shows the nanocomposite SEM analysis. It is spherically ordered, spherically arranged nanoparticles was observed, which resembles with the TEM analysis. However, embedding the nanoparticles into the polymer monolithic network, a monolithic single block of material with continuous macro meso network was noticed. The uniform dispersion of the nanocomposite into the polymer network was confirmed using a high resolution TEM analysis, and the uniform dispersion was further confirmed with elemental mapping, and the SAD pattern still shows the retainity of crystalline nature, even impregnation with the polymer network, and the corresponding weight percentage was calculated using EDAX analysis. Coming to the photocatalysis mechanism of the prepared zirconium oxide silver oxide nanocomposite, initially because of low energy band gap, the light energy was absorbed by the silver oxide, and the electrons will transfer from conduction band of silver oxide to conduction band of zirconium oxide. Thereby, it reacts with the dissolved oxygen present in the solution to form highly active peroxide radicals. However, the holes present in the valency band of both silver oxide and zirconium oxide reacts with the surface hydroxy molecules to produce highly reactive hydroxy species, which these peroxide and hydroxy radicals will participate in the degradation of norfloxacin antibiotic drug. That was we have taken for the degradation studies, and here majorly the peroxide radicals are more favorable than hydroxy radicals. That we confirmed from the trapping experiment. And coming to the various analytical optimization technique, here the pH3 is showing high photocatalytic efficiency. This is due to the electron rich center present in the norfloxacin drug, which leads to the electrostatic attraction between the positively charged surface moiety. So the high kinetics rate was observed at acidic pH3 when comparing with alkaline pH conditions. With the usage of 100 mg of photocatalyst, we can degrade nearly 30 ppm of norfloxacin drug molecule with a 2 hours of time period. In order to increase the reaction kinetics, we used a potassium bromate as a initiator sensitizer, which will trap the electron on holes generated from the reaction, and the different light intensity studies has been performed. Here 300 watt centimeters visible lamp was suggested for the all photocatalysis studies, whereas the 500 watts lamp also showing high photodegradation rate. However, the heat produced from the 500 watts will be problem for the photocatalytic system, and hence 300 watts was suggested. Coming to the conclusion of my work, here we designed a new class of heterogeneous zirconium oxide and silver oxide nanocomposite by using a sol gel and precipitation method, and the prepared nanocomposite was embedded into a translucent polyedema monolithic design via bulk polymerization technique. The prepared polymer monolithic silver oxide zirconium oxide nanocomposite shows a fast degradation rate towards norfloxacin drug under optimized pH conditions. Thank you for the patience.
Okay, Naveen Kumar. Now the talk is open for discussion. The participants, you can ask your questions. Okay, Naveen Kumar, you have mentioned that, right? Zirconium oxide and Ag2O nanocomposites is uniformly decorated, right? Can you please go to your some image of that? How you are justifying that?
Yes, ma'am. Here you can see the elemental mapping.
Why you are concentrating on
taken
this?
From uniform dispersion, ma'am.
Yes, I mean for photocatalytic analysis, right? You have used zirconium oxide, right? Decorated by Ag2O nanocomposites, and the uniform decoration is there, right? So what is
Yes,
the
ma'am.
necessity of going with that?
Yes, ma'am. The composite will be that zirconium oxide, silver oxide is a single nanocomposite. That composite we are dispersing into a polymer network, ma'am. This is an organic inorganic hybrid kind of photocatalyst. Organic template is polymer monolith, and inorganic material is the zirconium oxide, silver oxide photocatalyst. So because of that impregnation into the polymer network, it of material photocatalyst into the system. So macroporous network, the increase in photocatalytic efficiency also observed, ma'am.
Okay. Okay, Navid Kumar. Any other questions from the participants? Okay, no more question is there. Then we can move on to the next participant. Okay, anyway, thank you. All the best, Navid Kumar.
Thank you.
And the
Thank
next candidate, the next contributing lecture, Adivida S.R. Nair is available.
Hello, am I audible?
Hello? Yes, stop
Hello.
sharing your screen. Naveen Kumar,
Yes,
am
ma'am.
I audible to you?
Yes, ma'am.
Okay.
Yes, ma'am. I'm stopping.
Okay.
Stopping.
Okay, yes. The next contributing lecture, abstract number 959 and contributing lecture 44. Adivada S.R. Nair, you can please share your screen.
Okay, am I audible?
Yeah, we can hear you, but we cannot see the slides.
Just you open your PPT. So after that, you share through Zoom.
Yeah, now is it visible?
No, your screen is not visible to us.
No, I actually shared it already.
You open your PPT.
Yeah.
Open your PPT first. And keep the
Now it
PPT
must
as
be.
such. Yeah, now it is visible.
Yeah. Okay, so good
You can
afternoon to
proceed.
everybody. Okay, I'm Advaita Sanayar and my research topic is fabrication of cellular structure in thermoplastic polyurethane matrix using carbonaceous fillers. So in my presentation, a brief outline, I would be explaining on my objective, synthesis of both my nanofillers, how I had evaluated the synthesis and its characterization, preparation of polyurethane nanocomposites, the evaluation of the nanocomposites, and conclusion. The main objective of my study was the synthesis of nanofillers in which I've used graphene oxide and reduced graphene oxide. The oxidation of both graphene oxide and the reduction of GO was done by using XRD and FTIR Raman spectroscopy was done, while the morphological study was done by using SEM analysis. The synthesis of polyurethane was done in which the nanofillers were added in varying concentration, that is 0.5 weight percentage, 1 weight percentage, and 5 weight percentage. The characterization of nanocomposites was also done by using XRD, SEM, and FTIR. I have synthesized graphene oxide by using modified Hamas method as it is a safe and rapid method. As I have explained here in my synthesis process, here as we can see, sodium nitrate and potassium permanganate was used as oxidation agent, which will oxidize the graphite into graphene oxide, and the synthesis was done in acidic medium while keeping the temperature at less than temperature 15 degrees, so that the synthesis was easier and less time consuming. Here, addition of hydrogen peroxide will also bring a change in the color from dark brown to yellow color. This conversion will confirm the complete conversion of permanganate ion into manganese ion, which will also in turn represent that the reaction is complete. The powdered form of graphene oxide was obtained by heating at temperature 85 degrees Celsius. Further, the sample was collected and weighed. For the synthesis of reduced graphene oxide, hydrazine hydrate was used as the reducing agent. After treating the graphene oxide with hydrazine hydrate, I had washed with sodium hydroxide and then centrifuged and heated at 60 degrees Celsius. For the confirmation of the synthesis, I had used XRD analysis. As you can see that in graphite, there is a peak at 27.3 degree, which confirms the presence of the graphite sheet at 022 orientation. The disappearance of peak at 27.3 degree and the appearance of peak at 11.9 degree in GO that you can see in the image B. This confirms the complete oxidation of graphite to graphene oxide, while in case of C image, which represents reduced graphite oxide XRD analysis, we can see that there is a broad peak at 24.10 degree, which represents the plane at 002 orientation, and there is a less intense peak at 43.10, which represents the plane at 100 orientation. These peaks and intensities were compared, and then the confirmation of the synthesis was done. The morphological analysis was done by using SEM analysis, in which we can clearly see that the images of 2, 5, and 8 and 3, 6, 9, which represents GO and RGO, clear stacking of layers can be visible, and also both GO and RGO as compared to the graphite shows very inhomogeneous structure with lots of folding. The layers were also seen in the range of few to almost 10 nanometers range. Thus, a clear change in the morphology after the synthesis of GO and RGO was visible. The functionalization of the GO and RGO was done by using Raman spectroscopy. Here we can see that in the case of GO, there is a D band at 1358, which represents out of plane vibrations of sp3 carbon, while a G band is formed due to CC stretching, which represents in plane vibration of sp2 carbon, while there is a broadening of G peak and narrowing of D peak can be visible in the C image, which represents the RGO synthesis. The variation of position or intensity of G and D indicate the reduction of GO into RGO. Further, the synthesis of polyurethane nanocomposite was done by using solvent mixing method, in which the nanofillers and polyurethane were added to DMF. They were then combinedly added and heated to 90 degrees Celsius. After gel formation, the solvent, that is the DMF that was being used, was removed by decantation method. The gels were soaked in ethanol and heated to 30 degrees Celsius to remove the solvent. The morphological analysis of the PU nanocomposite was done by using the SEM analysis, and here it is clearly visible that in case of nanocomposites that where the fillers were added in lower concentration, the nanofillers are well dispersed and they are embedded into the polyurethane matrix, while in case of the nanocomposite where there is a higher concentration, there is a distinct morphology of interface can be observed, which indicate there is a weak interaction with the matrix, and also at higher concentration due to the agglomeration formation, the pores have collapsed, while in image 7 and 8, it is clearly visible that pore structures, or we can say the cellular structures, are properly visible. Thus, it can be concluded that at lower concentration, the polar structure or cellular structures could be easily obtained, which could be further used for various applications such as water absorption. Now, for the functionalization of nanocomposite was done by using FTIR spectroscopy. Here we can see that most of the apparent bands in unmodified polyurethane matrix occurred in nanocomposites as well, which indicate that not much change in the functionalities has occurred. Also, as clearly visible in image B, the lower transmitters with increase in the loading, that is, which is visible by the blue lining, that the nanocomposite with 5 weight percentage, the transmittance has decreased, which indicates higher population of bond, that is, a higher bonding of nanocomposites with the fillers. In conclusion, I have confirmed the synthesis of nanofillers. The morphological analysis was done by STEM, and also the porous structure was obtained at lower weight percentage. Thus, the confirmed successful synthesis of PU nanocomposite makes it a suitable candidate for further application. Thank you.
Okay, Adibada, thank you. Now it is open for discussion. The participants, you can interact. You can post your questions even in the chat box also.
So Advaita, what kind of
Okay, right,
cellular
sir.
structures are you going to concentrate? What kind of cellular structures?
Okay, so here actually I've obtained a cubical structure, although due to the concentration variation, I guess at 2 weight percentage, I could have obtained a more cubical cellular structure so that it could have been used. Here, although a clearly visible cubical cellular structure was not obtained.
Okay, so what is your future application for this material?
Okay, this material was actually the cellular structure could be used for water absorption.
Water absorption in the case you are going to treat, I mean, impure water or anything like that?
No, increased water absorption in the sense that this material could, like in water filtration, we could
Okay.
have used this material.
Okay, so can you comment on the optical properties of GO and RGO?
Excuse me?
Can you comment on optical properties of GO and RGO?
Actually, I have not analyzed on the optical properties, but there have been reports which suggest that it has a higher reflectance as compared to other materials, but I have not focused on the optical part.
Okay, thank you, Advaita.
Yeah, thank you.
Adivita, one more question from my side. That is, you have done
Yes,
this
ma'am.
analysis for different concentration, right?
Yes, ma'am.
Yes, right. So which are the concentration is showing a better result for this nanofilter kind of application? Why?
For nanofilter kind of application, since at 1 weight percentage, because in case of water filtration, the pores are very important. So I have actually done it at 1 and 5 weight percentage. Although in 1 weight percentage, the cells are visible, but I believe that at 2 weight percentage, although the SEM analysis has not been attached to it, but yeah, the pores are still visible. But as we reach up to the 3 weight percentage, there is a complete collapse of pores.
Okay. Any other questions from the audience side? If no more question is there, okay. Yes, all the best and thank you, Adivada. And we can move on to the next contributor lecture. It is contributor lecture number 45 by Madhu. Madhu is available. Yes.
Hello, good morning. I guess you can hear me, right?
Yeah, yes, you are audible. Please
Okay,
put it in the presentation mode now. Okay.
okay.
Yes, fine. You can
Yeah,
continue.
yeah. Thank you, ma'am. So I'll be presenting my work like we have done on the possibility of phosphate phases that we can stabilize during CO2 nanoparticle synthesis. Okay. So here my main aim would be like for the synthesis part, because I'm not going to concentrate more on the application part. Okay, so I'm Madhu. I'm working as assistant professor in Department of Physics at Siddhaganga Institute of Technology, Tumkur. Okay, so uh, we are just like 50 kilometers 60 kilometers from Bangalore. So if you I think most of you know Bangalore, and our place is almost like 60 kilometers from Bangalore. So Siddhaganga Institute is autonomous institute, which is mostly for BTech and MTech degrees. So so main aim here, what I try to concentrate is, so if you take your egg, most of you who are using egg for getting more proteins and stuff like that. So normally what happens, you have egg you have a white and also your yellow part, which is your yolk. So even if you take egg in US alone, around 200 million eggs would be put in trash, or like they will end up in landfill. And even in the previous 2 years, if you take UK, in UK they are almost disposing the 720 million eggs per year, just due to the fact that they are out of they have crossed the expiry date. So one of the work from Ajay sir lab in Rice University. So they have shown that this egg, whatever waste egg, instead of throwing it, instead of putting in trash, they have shown that this can be used for preparing a preservative. So a preservative coating to keep vegetables and even the fruits fresh. And this, as it is like a bio coating, there is no not much involvement of chemicals. So this is more of a safer way for coating. So in the same perspective, we were thinking like what are the other uses that we can look into this kind of waste, like normally waste. So for this, we try to synthesize cerium based materials. So by using self combustion. Okay. So what is the difference between your self combustion and regular synthesis? So self combustion, normally what we do is we take a fuel which is normally very good oxidizer, or it can be a reducer, and then we use a source is like, for in this example I'm using fuel egg as the fuel, and then the source is like cerium nitrate. It can be cerium nitrate if I want to use a cerium material. Or you can use different sources, like instead of cerium nitrate I can use cerium some other source. Okay, so like, for example, if I want to prepare iron oxide, I can use iron oxide, iron chloride, iron nitrate maybe. Okay, so these are different sources for that. This means normally this contains your basic element that you want to prepare. And then fuel, you can like a lot of people are doing a lot of biological fuels. So they are using a lot of extracts from plants, extract from some leaves. Okay, so even in this case we are going to use egg as the fuel. Okay, so whatever, instead of throwing, I'm using egg as a fuel. And then what we do, we just mix these two uh, precursors, like your cerium nitrate and egg, and then you just keep your this mixture at 500 degrees C for 20 minutes. So normally, as you saw in some of the previous slides or previous talks, you may have to use a longer time. If you use solid state synthesis, you may have to use for 10 to 20 hours. Or even if you go for hydrothermal, maybe again you have to go for longer time duration. So here it is very short time duration. And then in this case, what happens is your fuel will act as a self combustion, uh, or it will burn out by itself, and then it will give out the energy. So this energy would be sufficient for making a desired material. So in our case, we have not done any pre-heatment. So sometimes once you do this 20 minutes reaction, some people would again do a calcination at different temperature. But in our case, we are not done. It is just straightforward 500 degrees C for 20 minutes. So in this case, you have your material, whatever the desired material. Along with that, you have some byproduct. Mostly in our case, it is a oxide. It is a gas. Okay. So as we are using nitrate, there may be some nitrate gas which may be coming out. And in some cases, as this is a biological fuel, so we may also have CO2 which may be coming out in this reaction. So when you take CO2 or CuPO4, these two are very well studied. So I may not go into detail why we studied this, because if you take cerium phosphate, it is also well known for its luminescence and also UV absorption properties. And in some cases, they have also shown that for sensor application and also CO2 CO reduction. And if you take your cerium oxide, as a lot of even we saw very good talks in the beginning of this session. This is having a potential photocatalytic application. Along with that, some people they have shown for storage application as anode. And also this is quite good in for sensors and pigments. So I'm not going in detail about the application because of lack of time. I'll just try to concentrate only on the synthesis part. So when we do this synthesis, so first thing we normally check for the phase purity. Only then we can go for the desired application. So what we did initially is we take the egg as both, as I told, it has both white and also your yellow part, which is your yolk. So we mix it, we take some 3-4 eggs, and then we mix beat it up very well to get a good mixture. And then we take so normally when I talk about the synthesis, so in our case we are keeping this cerium nitrate concentration as constant. Like we take 1 gram of cerium nitrate, and then we add different fuel, different amount of fuel. So we start from 2 ml, 4 ml, 6 ml. So we increase the fuel. We keep our cerium nitrate as still as 1 gram. So that is the starting point. Then we do the combustion synthesis. So it is just 20-minute synthesis. Then you take your powder to the XRD. So when we do this mixed phase, mixed in the sense we beat white and also your yellow, we get a good mixture, and then what we do is we try to do the combustion synthesis, and we'll see what is the phase which has formed. So after 20 minutes, so we can see these peaks are broader, so it's good, like it is in a smaller size. But when you look into the phases, so when you have very low concentration of egg mixture, like 10 ml, then we normally have a predominant CO2. Then we have some part of CPO4 and also K2SO4. So these are the three different phases that we have, and as we keep increasing the fuel, so we still keep all the phases, all these three phases. But only thing, when we go for the higher concentration, like for your 20 ml or 35 ml, we have predominantly CPO4, which is your serum phosphate. So then we wanted to see what exactly happens if you just take only your egg white or egg yellow. So for this, what we did is we took only egg white, and then we tried to do the same, repeat the same procedure. We take 1 gram of cerium nitrate and then vary the white concentration. So we take 2 ml of white and then mix cerium nitrate in 2 ml of white, keep it in your furnace for 20 minutes, take it out, then see the X-ray diffraction. Okay, so then the same thing is repeated for 6 ml and 8 ml. So we change only the fuel, but we'll keep the source, like cerium nitrate is still 1 gram. So here you can see, like if you take the low concentration of like 2 ml, which is in the black, we almost get very pure phase of cerium oxide, CO2, with small amount of K2SO4. Then as we increase the white, so you can see K2SO4 peaks are growing up. That means the concentration of K2SO4 is also increasing. In all the cases, we are still keeping very good nanoparticle size. Like the particle size is around, when we do crystallite size, it's close to 15 nanometers. And we
Madhu,
have
you are having only 2 minutes.
Okay, I'll wind it up. Okay, so I'll wind it up.
Madhu?
Yes,
Madhu,
I will wind.
only
I'll
2
wind it up.
minutes is left out for you. Okay.
Okay. So next we have done some PDF, so I'll skip it. Then we took only the yellow part, and we do the same synthesis. So as we go for the higher concentration, like when we go for 4 ml and 6 ml, we have pure CPO4. So in the previous 2 ml, what happens is we have CuPO4, along with that we have some CO2. So if we take the higher concentration, only yellow, no white, then we get pure CPO4, serum phosphate. So this is what we have. So for pure phase, if you take only white, we get pure CO2. If you take only yellow, we get CPO4. And then we have also extended this for synthesis of iron phosphate and also cobalt and copper phosphate. Today, like in this, I showed only cerium phosphate. So these phosphate can be synthesized when we use yellow egg yellow or yellow yolk. Okay, so in conclusion, we can have egg yolk can be a fuel or the source for metal oxide phosphate systems. So this is what we wanted to show in this work. And in future, we are also extending the same thing to get LiFePO4, which is very good cathode lithium battery material, and also a NaFePO4, which is a very good sodium cathode materials. So with this, I thank you all for your kind attention, and also ICON 2020 SRM SIT for opportunity to present my work. Thank you. So I can take questions.
Okay, Madhu. Yeah, yes. Now the talk is open for discussion. You can raise your queries. Madhu, I have one fundamental question, that is, you are using egg as your fuel, right?
Yes,
What
ma'am.
is the significance of using egg as a fuel for what kind of an application actually you are looking for?
Main thing is I'm looking only for the phases. So like as I told, I want CO2. So once I get CO2, I can use.
Madhu, am I audible to you?
Yes, ma'am. Actually, I'm
Madhu?
answering. Hello. Yes, ma'am. I'm trying to answer. So, CO2 is good for photocatalysis, and CPO4 is good for luminescence. So, these are the properties that we will actually look. But only thing we were looking to stabilize a given phase. Like I want to stabilize CO2, so I use for this we use only white, and if I want to CPO4, I use yellow. So this is what we have. And if we take CuPO4, it can be used for luminescence property. It's very good for luminescence. And cerium oxide, as it has been already demonstrated, is good for photocatalysis.
Okay. Any other questions from the participant side? Okay, so no more question is there. Thank you, Madhu. All the best.
Thank you,
With
ma'am.
this, we are concluding this session. So before concluding, I would like to thank the chairperson of the session, Dr. Jerry. Thank you for sharing the session, sir. So with this, we are concluding this one. Thank you, one and all. Thank you.
Thank you, Professor Jellal, and thank you, Professor Peng and Professor Lee, and thank you, Kalamam, for making this session very beautiful. And I have one more announcement that we have a session in the afternoon for this HCMS symposium, that is session 4C. We will there where we will have excited talk by Professor Abhishek Kumar Singh from IISc Bangalore, and he will be talking on machine learning assisted discovery of novel materials with targeted properties. And see you by 4:45 p.m. So kindly join us in that session. Thank you so much.